Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help demonstrate how currents can kind of interact, creating forces in between wires. So what we're looking at here, we've got this wire here that we're going to assume to be a long straight wire with a current I1 in the upward direction. Over on the right we've got a current loop that carries a current I2 clockwise. I've got dimensions W and L for the width and the length of this current loop. It's at a distance A from the wire. Now it's important to realize that this current loop is in the XY plane of the coordinate system that I have defined right here. Now the idea is that the current I1 is going to create a magnetic field over here, and then that magnetic field can interact with the current I2 by the magnetic force, which is IL cross B. Now, before we talk about what's happening here force-wise, it's very important to understand what the magnetic field lines around this wire look like. So I'm going to take a moment here. I'm going to just move this off to the side, just temporarily. And we're going to focus on just what the field lines look like around this wire. So magnetic field lines around wires are circular, and you tell which way by right-hand rule. So the magnetic field lines around this current look something like this. So I'm going to draw three of them. And again, the closer to the wire, the stronger the magnetic field. So I guess I'll put one more in there. All right. And to tell which way, you just kind of mentally grab the wire with your thumb in the direction of this current, and then your fingers will roll around in the direction of the magnetic field lines. So the magnetic field lines in this example are pointing like this. Now, what that means, over here to the right, if I were in the XY plane and I pick a spot like right here, the field line is basically pointing in the same direction that you're looking as you watch this video. So that would be the minus Z, or sometimes we would say the minus K direction as far as this coordinate system is concerned. If we were over here in the XY plane, the field lines are coming at us. If we were like in front of this wire looking at this field line, the magnetic field vector would point to the right in the plus I direction. And if we were behind the wire, the field line behind the wire over here, like tangent to this curve, would point to the left. So when we take our current loop and we put this somewhere close, I'm just going to put it right here for now. Actually, no, distance A away. All right, hold on, I'm going to get rid of these. I'll just put one magnetic field vector, or field lines. So the field lines are looking like this around the wire, but again, there's many, many, many of them. It's important to realize that anywhere along here, those field lines are in the minus Z direction. I'll go ahead and put this guy in this region here at distance A away. So what that means is that the magnetic field vectors along this region right here point this way. I'm going to go ahead and put some vectors in there, and again, these crosses represent vectors pointing away from you. Now, in this region, they also point that way. In this region, they also point that way. All the magnetic field vectors on this side point in the minus K direction. But over on this side, the field is weaker, so I'm just going to put a couple of field lines there. I guess I'll put three. And I'll add a few more over here. All right, so we have a relatively strong field here, relatively weak field over here. That's because the magnetic field strength falls off with distance. So the further we are from the wire, the weaker the field. Now you also notice I didn't bother putting magnetic field vectors along here. I'll talk about why here in just a minute. All right, so now we've got this current I2 here, and I'm going to kind of focus now on this length of wire. Because we have a current I2 in a magnetic field, we're going to have an IL cross B force on it. And the direction of that force we get from the cross product. So you put your fingers in the direction of this current, which would be basically straight up on the screen. All right, right hand, you rotate till you can sweep towards the minus K direction, because those are the magnetic field directions. And what you should conclude is the magnetic force on this branch is to the left. I'm going to go ahead and draw a force vector. Now, that force is given by this cross product. This I is going to be I2. The L is going to be the length of this wire. The B is going to be the magnetic field along here. Now I'm going to put a 1 on this because this magnetic field is coming from current 1. Right? Then times the sine of the angle between the IL and the magnetic field. So the IL vector, or sometimes just called the link vector, it points in the direction of the current. And the magnetic field's minus k direction. Angle between them is 90. Sine of 90 is 1. So here's an expression for the force on this wire branch. Now this magnetic field vector is coming from this current. So if we treat this like a long straight wire, that force vector would have a magnitude of mu sub O over 2 pi I1 over the distance between this wire and this point, which is what I have labeled as A. So this force vector is to the left. It's equal to I2L times B1, where the B1 is given by this expression here, mu sub O over 2 pi I1 over A. Let's chat about this wire now. So there are, in fact, magnetic field vectors along there. I'm going to go ahead and draw at least a couple of them, or at least one X there and there. Now, here, the current is to the right. So when you do the IL cross B, you're going to get a direction that's up. Right? Because your fingers would point to the right along this path. Magnetic field vector still minus k direction. When you do the sweeping, your thumb will point up. Now, if I come down here, at this point the current is to the left. When you do the IL cross B, when you do the direction, you're going to get a force that points down. These forces will have the same magnitude because it's the same magnetic field strength. Now, it turns out the magnetic field strength varies along here. It ends up being, an integration type of problem to find that force. But the magnitude of this force and the magnitude of this force are the same, and they are in opposite directions. So the net force is going to be 0, so I'm not even going to worry about these. I should talk about this guy, however. So the current direction for I2 is down. When you do the I2 sweep towards B for the cross product, you should conclude that the force is to the right by right-hand rule. So again, you put your fingers in the direction of this current, rotate your hand till you can sweep towards the magnetic field vectors, which are in the minus k direction, or just rotate your hand until your palm basically is pointing in the minus k. Your thumb will give you the cross product direction. Right-hand rule is a little hard to show on this computer screen. This force is going to equal, again, it's going to be an IL cross B force. So the I is going to be I2. The L is the length of this wire. The B is going to be the magnetic field created by wire 1. I'm going to go ahead and put a B, I'll put a 1 on that, but again, it's not the same as this magnetic field. Maybe I should go back and maybe put maybe an L on this for the field due to wire 1 on the left, and over here field due to wire 1 on the right, I guess. Subscript not super important, and I don't want to overcomplicate the video, but in fact this magnetic field is not going to be the same as this one because we're further out. Okay. Again, the angle between the current and the magnetic field in this picture right here is 90. Sine of 90 is 1. So this force is going to equal I2 times the length of the wire times this guy, which is the magnetic field produced by I1 all the way over here. So treating it like a long straight wire, mu sub O over 2 pi I1 over. Now the distance is the distance from here to here, which in my picture would be A plus W. Now, you notice that I drew this force vector a little bit shorter than this one. That's because I knew by observation here the length is the same, but the magnetic field is weaker, so I knew that this force vector would be larger. So the net force is the vector sum of the two. Because this one's the larger force, this thing would in fact accelerate to the left. I'm going to use my standard rule of thumb then and call left the positive direction. So that would be this force vector minus this one. And I'm going to just write these exactly in the order that I have them. But you could group these any way you wanted. And here is an expression for the net force. That net force is to the left. If I want to make a vector out of it, we could say minus I direction with respect to that coordinate system. So the point of this video was how to show how wires interact, wires with currents. I hope that this video successfully does that for you. Have a great day.